When you hear the term artificial intelligence, it is easy to picture a monolithic, sentient brain housed in a server room. In reality, the field is a collection of specific engineering disciplines, each optimized to solve a very different type of problem. To build these systems, engineers first had to establish a baseline. For decades, that baseline was us. Human intelligence is defined by our capacity to acquire new knowledge, adapt our behavior to unpredictable situations, and apply skills to achieve a goal. A human can perceive, predict, and manipulate a highly complex world. The historical challenge of computer science was figuring out how to program a rigid machine, like these early mainframes, to execute this exact cognitive flexibility. Before you can engineer intelligence into a machine, you run into a foundational problem. You have to explicitly define what success actually looks like. This gives us our first access, the benchmark. Do we judge success by how closely it mimics human behavior, or against a standard of mathematical rationality? The second axis is modality. Are we evaluating its internal thought process, or strictly its external actions? This table shows the resulting intersection. By mapping these two axes against each other, we get a 2x2 matrix. This grid establishes the 4 distinct perspectives that govern all artificial intelligence development. Understanding where a technology sits on this matrix explains why a conversational chatbot operates so differently from an autonomous vehicle. They are quite literally engineered for different definitions of success. Looking at the top left quadrant, we have the thinking humanly approach, also known as cognitive modeling. The methodology here is highly biological. It attempts to reverse engineer the human brain by relying heavily on insights from neuroscience and cognitive psychology to structure the machine's programming. A clear example of this was IBM Watson in 2011. By modeling human cognitive processes, Watson used natural language processing to analyze vast amounts of unstructured data, allowing it to reason through complex Jeopardy questions well enough to defeat human champions. This cognitive-inspired approach laid the groundwork for deep neural networks. By mimicking the physical structures of biological neurons, these networks process information in a way that enables modern speech recognition and computer vision. Moving directly down to the bottom left quadrant, we find the acting humanly perspective, historically driven by the Turing test. The core philosophy shifts here. In this quadrant, the internal reasoning process is entirely irrelevant. The system achieves success if its external actions and outputs are convincing enough to fool a human observer into thinking they are interacting with another person. Consider the milestone in 2014, when a chatbot named Eugene Gershman reportedly passed the Turing test. It succeeded by accurately mimicking the conversational quirks and limitations of a 13-year-old boy. This requirement to act humanly is the exact engineering foundation for the virtual assistants and large language models we use today, like Siri or ChatGPT. They are optimized purely for human-like interaction. While modeling human behavior is highly effective for user interfaces and psychological research, human brains are inherently biased and prone to error. To solve problems requiring absolute precision, engineers had to look for a standard higher than simple mimicry. That brings us to the right side of the matrix and the thinking rationally quadrant. This is often called the laws of thought approach. This perspective abandons human biology entirely. Instead, the focus is on formal logic and strict mathematical reasoning. The goal is to build a system that guarantees correct inferences. In the 1970s, a system called Mycin demonstrated the power of this approach. It was a rule-based expert system that used formal logic chains to analyze patient symptoms and diagnose bacterial infections, frequently achieving higher accuracy rates than human doctors. But the laws of thought approach has a fatal limitation. The real world is messy. When faced with unpredictable environments, incomplete data, or uncertainty, strict logical frameworks break down because they cannot compute absolute truths. To overcome this, the field shifted to the final bottom right quadrant, acting rationally, or the rational agent approach. A rational agent does not limit itself to proving logical statements. It is designed to perceive its environment and execute specific physical or digital actions that maximize the probability of achieving its assigned goal. When DeepMind's AlphaGo defeated the world champion in 2016, it wasn't mimicking human strategy. By analyzing the complex arrangement of the board through reinforcement learning, it discovered optimal moves in a game with near infinite possibilities, far exceeding human intuition. This same framework dictates how a self-driving car processes its surroundings to navigate obstacles. It requires split-second optimal decisions, not perfect internal logic. Today, acting rationally serves as the standard for modern artificial intelligence. This approach prioritizes achieving optimal real-world results over the specific need to imitate human cognition. To engineer a rational agent, developers define 4 criteria. First, the performance measure, the mathematical criterion for success. Next, prior knowledge of its environment and the specific actions it can perform. Finally, its percept sequence, the continuous stream of collected data. This establishes a continuous interaction loop. Sensors act as the agent's eyes and ears, pulling in raw data from an unpredictable environment. That data is processed, and a decision is executed through actuators, the mechanical motors on a robot that allow the agent to alter its surroundings. This diagram outlines the ultimate iteration of this architecture, the learning agent. Rather than relying solely on pre-programmed knowledge, this agent adjusts its own rules over time to survive in unknown environments. Inside the system, the performance element is responsible for taking current data and executing baseline decisions. But immediately after an action is taken, the critic module evaluates the outcome. It measures the result against the performance standard, generating strict feedback. That feedback passes to the learning element, updating internal knowledge, while the problem generator forces new, exploratory actions to discover efficient strategies. True artificial autonomy moves beyond pre-programmed instructions. Success requires a recursive architecture that evaluates its own failures and adapts its behavior to maximize results. Zooming out to our 2x2 matrix, we see how these fields fit the 4 perspectives. The left side, thinking and acting humanly, gave us cognitive modeling for neural networks and chatbots. The right side, thinking and acting rationally, produced logical expert systems and optimal autonomous robots. So the next time you interact with an AI tool, ask yourself where it belongs on this grid. Is it trying to talk to you like a person, or is it trying to quietly execute an optimal task? Ultimately, artificial intelligence represents the engineering of distinct logical tools, each designed to conquer an entirely different definition of success.